So we resume today the discussion of the quantization of electromagnetic field, and in today's class we will try to see achieve the quantization procedure completely. So recall in the last discussion session we had the handle on our Lagrangian or the action of the theory which used to give me the correct equations of motion, the box of A mu is equal to 0, which constitutes the two dynamical sets of Maxwell's equations. And we can see that the action of interest was this object where F mu nu were contracted amongst each other with -1/4 factor, and with some massaging of the equations which we have seen previously due to their antisymmetric nature and the contraction with respect to the eta mu nu's, which come handy in writing this kind of things. One can rewrite the whole action in terms of boundary terms as well as terms dependent on the A's directly. Previously, when I am writing F mu nu, all the terms are appearing contain the derivative of A mu's. There is no free term which has a derivative which is free of the derivative of A mu. So since in the variational approach I want to get an action which has a free A mu, I can convert it into a boundary terms minus something which contains a free A mu, and with respect to the variations of A mu, we obtain the equations of motion, which is the box of A mu is equal to 0, which is equivalently del mu F mu nu is equal to 0 or del mu F mu alpha is equal to 0, where alpha is a free index. So that we have seen in the previous class. An exercise, a set aside exercise for you was to clearly verify that the action can also be written in terms of dynamical degrees of freedom which are physically observable, electric field and magnetic field, which is nothing but E square minus P square. So remember, we are writing these things in the units of epsilon naught is equal to 4 pi epsilon naught is equal to 1 and C is equal to 1 as well. So otherwise there will be some dynamical dimensionful constants in this action. So in the previous class itself, we realized that del 0 A0 never appears in the Lagrangian, so its conjugate momenta corresponding to A0 is 0. But for remaining three AIs, their time derivative appears in the Lagrangian, so we can define the momenta corresponding to them, and we obtained that the electric field is the conjugate momenta corresponding to AI. So AI electric field pair has a Poisson bracket structure. Okay, using that I can write down in the phase space what would be the Hamiltonian which governs the theory, and we obtained a piece of a Hamiltonian which was the field strength, the energy density of electric field, energy density of magnetic field, up to a piece which we were worrying about what does it mean, because presence of that term with a minus sign was not very convincing for us, because this runs a risk of converting the total Hamiltonian negative, and maybe then we would have to demand new structures in the phase space like what we had done for the Dirac fields. So in this class, let us try to see how to handle that, and ultimately it turns out that it is not very difficult term to handle, at least on the equations of motions of this theory. Because if I take, let us say, the Lagrangian or even the Hamiltonian, if you want to use Hamilton-Jacobi equations, both of them are equivalent. So take any of them. Take either the action in terms of Lagrangian, or you take the Hamiltonian and obtain the Hamilton-Jacobi equation. That means the equation of motion with respect to A0. You do del S upon del A0, or you put del Hamiltonian upon del A0. Both of these things should give us some equations of motion which would effectively tell you about how the different terms are evolving. So in this thing, they should tell me the rate of change of the conjugate momenta associated to A0, P0 dot, and similarly here, P0 dot, if you remember, in the phase space, or call it pi 0 dot in the phase space, should be written like this, okay, with a minus sign. So if I want P0 was supposed to be 0 in on the Lagrangian or even the phase space, there was no P0 which did not arrive. Lagrangian did not depend on A0 dot, and that is the characteristic of the physical theory, that P0 is 0. And if I want my P0 to remain 0, that means I'm on the physical surface all the time. My dynamics does not take me away from the electrodynamical's description, because electrodynamical description is always pi 0 should be 0. If that is the demand we enforce, that means Hamiltonian's derivative with respect to A0 should also be 0. This would be the requirement of keeping this equation intact under time evolution. If that is the demand we enforce, then we get from the variation of the Hamiltonian, or equivalently the variation of the action with respect to A0 will yield me an equation like this: del I F0 I is equal to 0. That is equivalent to del I EI is equal to 0, which can you straightforwardly see from this Hamiltonian approach. So this is a demand which goes by the names of Gauss's law in vacuum. And this is a enforcing demand of a constraint. The constraint was this: pi 0 was not to be appeared in the physical description of the system, and the demand is that under time dynamics pi 0 should not turn on, because that is the description of electrodynamic field. This is the description of the action of the electrodynamic field. Under time evolution you do not want to destroy that, so you want pi 0 dot remains 0, and that is equivalent to this new constraint which one should enforce, that del I EI is equal to 0. So both action approach wise pi 0 dot is this, or Lagrangian Hamiltonian approach was also pi 0 dot would be minus of this. Both the things are equivalent. Putting them to 0 will give you this Gauss's law. So Gauss's law is really not a dynamical law, but just telling you the constraint of remaining on the physical surface of the Hamiltonian, or on the phase space, describing the electromagnetic theory correctly. So if that happens, that means this term is not a worry anymore. On those surfaces where physical dynamics is happening, that is you're on the real physical surface in the phase space. So remember, let us draw phase space. So there will be some surface initially which was pi 0 is equal to 0. Phase space is made up of A1 pi 1 pair, A2 pi 2, A3 pi 3, and A0 pi 0. All A1 pi 1, A2 pi 2, A3 pi 3, you are free to explore under time evolution. They are not constrained to be anything. But pi 0, one of them has to be constrained, that this is the dynamics. This surface pi 0 is equal to 0 is a surface which are hypersurface in higher dimension where the electrodynamical theory lives. Okay, so you do not want to leave that surface. That is this constraint, and therefore one can drop the last term in the Hamiltonian, which tells you if it is non-zero, that means you have moved away from the physical description of electrodynamics. So I do not want that. Under time dynamics, I want to remain there only. So therefore I can constrain myself to remain on that physical surface that is equivalent to Gauss's law, and under that physical surface the Hamiltonian becomes just E square plus B square with a half. And now that is a relief for us, because this is a positive semi-definite Hamiltonian. This does not become negative ever. So at least on the physical surface, I am guaranteed to get a meaningful Hamiltonian, and therefore I should not be worrying about the negativity of Hamiltonian, which bugged me in the Dirac fields case or spinor field case. Okay, so from now on we will work with this Hamiltonian rather than the previous terms, ensuring that on physical surface we are doing the business. Remember, we are not using equation of motion. Since we are going to do quantum dynamics of this, we should not be using classical equation of motion. So you might wonder that why to use classical equation of motion for doing quantum mechanics, but remember, we are enforcing the what you would have called equations of motion on A0. This is the equations of motion for A0, and A0, remember, was not a dynamical variable of our theory. Del 0 A0 never appeared in the Hamiltonian, so therefore the A0 was not a dynamical quantity in our theory. This was just a free fiducial object which has appeared in the Lagrangian. It does not have a real time dynamics. It's something called gauge degree of freedom. So therefore, I am not fixing the dynamical variables A1, A2, A3, or E1, E2, E3, B1, B2, B3. All I'm fixing is the dynamics of the space of pi 0. Pi 0 I should not evolve in time. Okay, so with this understanding, we will move forward and try to see how can we explore this the remaining degrees of freedom judiciously, so that we get to the quantum portion of the electrodynamics. Remember, in the doing the business so far, A0 has been declared to be unphysical, meaning not really physical variable. It is just something which we can exploit, just like its conjugate momenta we have exploited right now. So real degrees of freedom which are going to be witnessable are made up from A1, A2, A3 only. So already now we have a 3 degrees of freedom describing electrodynamics. Later on, we will see one of them also goes away. So ultimately, electrodynamics is going to be described only with 2 degrees of freedom. Okay. Now, further we recall that while we were discussing electrodynamic structure, we had another freedom gauge freedom in redefining my phi and a up to some scalar function f. So to phi could have been rescaled by taking phi minus del f upon del t for any arbitrary function f. F was not constrained to be any particular function. And also under that, we had realized that a can be shifted to a plus the the gradient of f. So under this gradient of f and temporal derivative of f, the a0 component and a1, a2, a3 components can be shifted by choosing any arbitrary function f. The electrodynamic structure does not change under this selection of f. Also, we wanted that there should be a gauge condition where I kill off the terms which are appearing extra in the dynamics of vector A. So remember vector A, the box of A plus some extra quantity were appearing uh, if I just do the computation of curl of A. Those extra terms can be switched off by demanding this. So therefore, we would have thought that we thought that time that we could take the freedom at our hand, choosing f in such a way that this whole term can be killed off, and ultimately I get the wave equation for all the components a0, a1, a2, a3. Okay, and this we know can always be done. However, in following discussion, we will do it slightly more carefully in order to make contact with the physical more obviously. Meaning there are various ways of selecting this condition. This goes by the name of a Lorentz gauge. But now we are going to work in something called the Coulomb gauge, which is a equivalent description of this while in 2 steps. So let us try to see what do I mean. So first, suppose initially I am starting with a pair meaning the scalar and the vector potentials. Vector potential is a0 and the scalar potential is phi naught. And I want to choose some function f such that I achieve this goal, let us say. So I would therefore take a function f, which is a function of t and x both. So at any time t, I'm going to use the function f as such. And this is my choice. I will take the phi naught which is provided to me. I will integrate it over some time up to time where I want to do my computations and get a function of t and x. This is a function of t and x. This is also a function of t and x, t prime and x. So what I'm doing, I'm just doing the temporal integration up to a time t where I want to know my function and I want to achieve this. At different times, different functions would do that. That means different values of this function will do that. That is fine. So I will get a functional form in time t. So let us do that. So do this integration up to the symbol t, such that when I do del f upon del t, when I take the partial derivative, I will see that the partial derivative time is only appearing in the upper limit over here and everything else is a dummy variable. It is getting integrated over. So del f upon del t is just phi naught. So what I have done, I have taken the integral of phi naught as my function such that del f upon del t is just phi naught, which is fine. So therefore, if I do that, I know after doing the gauge transformation with that f, I will land up on the case where phi has vanished. In the new gauge, the phi has vanished. Initially, it was phi naught. I did this gauge transformation. I ended up phi being 0. That is, a0 has been achieved to be 0 in this new gauge. So at least this part of this computation, I can go to a frame where phi has vanished completely. So then I will be worrying about only that part. Now separately, I could have done the other way as well. I could have chosen another gauge where I killed off the second term. That means divergence of A initially would have been something. Let us say when I chose, my initial starting split up was phi naught and A naught. So there was no guarantee that divergence of A naught is 0. It could be anything, so non-zero number. So if that is the case, under gauge transformation, divergence of A is supposed to change by the Laplacian of F. Remember, the A was itself supposed to change through a gradient term of f. So therefore, the divergence of A will change with Laplacian of f. So that is what it would happen, and I want it to be 0. I want it to become 0 in the new gauge. This is my demand, let us say. That means f has to satisfy an equation which is Laplacian of f is minus of the divergence of the old a, the previous a naught before the gauge transformation. So this can be taken as a source function for function f. So called it some source function j. And remember, given this structure, Laplacian of some function is equal to some source function, ends up giving you solution through the green function approach, that the function itself will be 1 upon 4 pi times the source function integrated with the green function of the free space, and the green function of free space is 1 over x minus x prime. So what I'm doing, I'm taking the source function jx, make its variable x prime dummy, divide it by x minus x primed mod, and integrate over the dummy variable x prime. This I claim, this f which I have written as an integral form, I claim is a solution of the equation which I am demanding. This equation has this solution that you can verify quickly, such that if I take the Laplacian with respect to x. So remember, this Laplacian is with respect to x. So the Laplacian will go and search for x dependency. This is x prime, this is x prime, this is x prime. Only x dependency is coming over here. And you know from your electrodynamics course, the green function approach, that the Laplacian of 1 over x minus x prime is just the delta function with a minus 4 pi. So that Laplacian acting on this x minus x prime will give you a delta function in x minus x prime, and that integration will exactly convert it into the equation which we are demanding. Therefore, this is a good solution in free space. The green function in free space is 1 over x minus x prime. Okay. So therefore, I can choose my function this. If you give me initial a naught, I will compute its divergence, put it here, do this integration, and whatever comes out, I will declare it to be my f, and I will do the gauge transformation by that. And you know, once I have done the gauge transformation, its Laplacian is going to be minus of divergence of a naught. Therefore, in the new gauge through this f, the divergence of new a will be 0. So I could have killed off the divergence term as well. In the previous example we saw, if I chose the integral version of the phi naught, I could have killed off the phi, which is appearing over here. Or the second approach is that if I knew what is the divergence of a naught, I can kill off that term as well and can go to new gauge where this term is 0. And it so happens these two conditions are not different. They are one and the same condition under certain context. And that is what one should be able to realize just by staring at the Gauss's law. The divergence of E should be 0. If divergence of E is supposed to be 0, let us say, that should be true in all the frame. Electric field does not change under gauge transformation. So E does not change from E naught to E. E remains the same under both the gauges. So in the previous gauge where I had not selected any F, then the electric field would have been defined in the pair of phi naught and A naught. Okay, and the divergence of electric field would have been obtained from the Laplacian of phi naught and the divergence of A naught. And that should have been 0 from Gauss's law. Okay. So that means again, I can write down this as the equation of Laplacian of phi naught is equal to minus of del upon del t of divergence of A naught. This equation should have been true because of Gauss's law. Again, uses this as a source function, divided by x minus x prime, integrated over d3x prime, just like we did for this thing. We see that in any frame, any gauge, phi naught can be obtainable from the divergence of A, because divergence of A goes here, sits in the derivative place, its integration is going to fix what is phi naught. This is always true. In any gauge, this will be true. So therefore, if I choose a gauge where divergence of A vanishes, then this left hand side will also vanish. That means choosing divergence of A is equal to 0 over here, go to this gauge, will ensure that divergence of A is 0, and Gauss's law will ensure that as a result, phi will also be 0. So therefore, I choose this gauge where divergence of A is 0, phi will automatically be 0, and this condition will also be satisfied automatically. So that is the Coulomb gauge. Okay. In the Coulomb gauge, we can write down the wave equation just what we wanted. Phi becomes 0 and divergence of A becomes 0. If phi becomes 0 in the new gauge, this term in the new gauge will not be present. So electric field will be totally obtainable from the temporal derivative of the remaining A's. A0 or phi has been put to 0. So therefore, only vector quantities are going to determine your physics in this gauge. So electric field will be minus of del A upon del T, and magnetic field, like before, will be curl of this A. So far so good. So let us go ahead and try to see that once we have set up the wave equation, because in this case the condition of getting wave equation is automatically satisfied, so we can indeed write down box of A mu is equal to 0. It so happens that A0 is 0, so therefore that will not be a physical quantity. Physical quantity will be the remaining non-zero AI. So what we really are after is the solution for the box of AI is equal to 0. Now we have a 3-component object AI whose wave equation we are trying to solve. So previously we had solved for scalar field single component object and the 4-component object for Dirac field. Now we have at hand in this gauge 3-component object AI whose wave equation is the story of electrodynamics. Okay, this is fine, and let us go ahead. We already know, I will not waste time in again obtaining the solution of the box equation because we have solved it too many times. So I know ultimately it so happens that on the exponential the plane wave structure comes about minus et plus vector p dot x vector x. So I am collectively writing as a 4-dimensional dot product p dot x. With plus p dot x, I mean the energy comes with a negative sign. With minus p dot x, I will say the energy comes with a positive sign. So therefore, I know it has two solutions, either with positive frequency or energy. You call the energy in terms of p mu's, p0, not the Hamiltonian energy of this field. So this plane waves energy, not physics, the field's energy. So this P can have two solutions. This is massless Klein-Gordon equation. There is no mass term. So P0 is related to the remaining P1, P2, P3 with this relation. Magnitude of P times C is P0. And it will come with a sign plus minus sign actually. Plus minus sign of both. So it can have a positive energy solution, positive frequency solution, or negative frequency solution as before. That is fine. Now we have as well seen that divergence of A is supposed to 0, which can be written as del I AI is equal to 0. If I do that and take one plane wave from here with a definite momenta P, doing this derivative will show me that AI, the quantity which is appearing over here, is getting dotted with P. So this is the component, first component is obtained by first component of this, second component is obtained by second component of this, and third component of this is obtained by third component of this times the exponential function. But vector property of A is captured by vector properties of small a. Small a is the vector quantity, it has component, and multiplied with this plane wave gives you a vector AI. Once I take the divergence of this A, you will see that the P will get dotted. P coming from the spatial derivative of this exponential function will bring down a P, and dotted with this vector A dot P will appear. Should be 0, which in component form can be written as A of I index gets contracted with a Pi index, that should be 0. So you see that the vector A, which is appearing over here and giving a vector character to the capital A, the gauge field, is orthogonal to the direction of a propagation of your wave. So therefore, we initially wanted to start the discussion with 3-component object AI. It so happens that all 3 components are not independent because vector A cannot be arbitrary. Vector A has to maintain a relation that it is orthogonal to vector P. That means A dot this is equal to 0. This suggests that if you know the propagation direction, then I have a relation between A1, A2, A3. If you know what is P and you know 2 of A1, A2, then A3 will be automatically determined. So all 3 quantities are not independent quantities, only 2 of them are really independent. So if I choose my axis such that my direction of propagation is z direction, then I know that the vector A can lie only in xy plane because it has to be perpendicular to the p direction. That means it will have two components only, and therefore the vector A also for a given plane wave can only lie along xy direction. So therefore, if P is chosen along Z direction, A of P will only along be X or Y. So it will reduce the problem to ultimately 2 degrees of freedom. So therefore, the story of electrodynamics, which we thought is a 3 degree of freedom object, looking at the structure, the divergence of A is equal to 0 condition is actually suggesting me that in this gauge, only 2 degrees of freedom remain physical. Therefore, we've discussed a theory. Electrodynamics theory is a theory of AI where only I can take two values, or call it AR. AR lies in the plane. So this is a plane and this is a propagation direction P. So your A can take any direction in this plane. So this is the condition R. R can take value 1, 2 in the plane. So AP can be written, vector AP can be written as AR ER, where ER is a unit vector in the plane. Okay, so let us write it down as a full theory. As we know, only it could have two components along x or y direction. The vector A, the full vector A can only project along x direction or y direction. So therefore, the full A, which we are looking for, the capital A, the gauge field, is some vector times plane wave multiplied in xy plane. And since we want the gauge field to be the vector potential to be a real quantity, because magnetic field and other things are going to be obtainable from this, temporal derivative of this will give me electric field, spatial curl will give me the magnetic field. So therefore, better this not be a complex quantity. So therefore, I will add a complex conjugate to this. So I will obtain this plane wave, as you know, is not of real quantity. Its complex conjugation has to be added. So I take this solution, the first line of this object. I take this solution. This is a valid solution of wave equation which points in the xy plane. Take its complex conjugate. I get the full real vector potential A, and I want to do business with that. Compactly, the whole thing can be written. Since this has two objects appearing over here, I can collectively call it E lambda, where lambda takes two values, 1 and 2, 1 for x, 2 for y. So I can write down the whole lengthy kind of expression as this, as a simple as AP lambda, where lambda will again tell me what coefficient I'm coming with the direction EX, and 2 will tell me what is the projection along direction EY. So therefore, compactly, the vector potential is written like two component vector and its complex conjugation like this. So this is my dynamical description of electromagnetic theory. And now we know, once we have solutions of equations of motion and everything, and we know it's a oscillator story in momentum space, everything of the scalar field or the Dirac field which we have learned is applicable to these 2 degrees of freedom as well. Apart from counting the degrees of freedom to be 2, all the other story of the Klein-Gordon equation which we have learned throughout will be applicable to these 2 degrees of freedom as well. So therefore, I can quantize the systems as a harmonic oscillator system in momentum space again. And in that process, these things will become operators. So I cut short the story. That is the same story which we have learned far too many times by now. And we know now that the, the vector potential can be written as operator this here, and its Hermitian conjugate, because it has become operator, so it will become Hermitian conjugate. So A lambda daggers will appear. Again, lambda take value 1 and 2 for two polarizations in the plane. P is the momentum corresponding to the oscillator which we are talking about, and this is the mode function which is satisfying the oscillator structure. In addition, there will be a polarization vector which is coming about, which tells you in which direction A is indeed uh, pointing, depending upon how many excitations along the x direction, how many excitations along the y direction. Collectively, I will get to know what is the overall polarization of this quantum field if I put it under some state. If take its expectation under some state, That means that will give me expectation of this and expectation of this operator. That will decide my polarization. And as you can see, these are operators. The expectation will have some variances as well, fluctuations as well. So therefore, whenever I say expectation of the vector potential is this much, I am only talking about polarization has an expectation behavior in that direction. There will be fluctuations associated with it due to quantum character of A and A dagger. Okay, so now I have become, this has become a vector potential but quantum mechanical in its nature. So I do not have a definite direction of polarization. I have only expectation and variances. However, the story which we have learned that propagation direction P and the plane of the polarizations are all orthogonal to each other. So therefore, in three-dimensional space, the propagation directions unit vector, which is P upon magnitude of P, E1 and E2, provide you complete basis in the three-dimensional space. So that means if I take the outer product of the three unit directions, that should sum up to identity. So that is the mathematical statement that the basis vectors in the plane and the basis vector along the propagation direction, sum or outer product of that is equivalent to delta ij. This is that statement. The total E in the three-dimensional space summed over I running from 1 to 3 should be identity, which is this box. And from here you can see that in plane, if I just focus on the what is the relation of the plane basis vector, in the plane the two basis vectors sum up to delta ij minus the third direction. So this is the projection operator into the plane. That is the plane's orthogonality relation. The planes, any vector in the plane can completely be described by these two vectors only. So therefore, their completeness relation in the plane, completeness relation in the plane can be written as completeness relation of the full three space minus the unit direction of the third thing. So that means ERES outer product. So R running from 1 to 2 is equal to identity minus the E3 outer product. Okay, so that is this equation where RS, so you can write down this thing as a delta RS, where you have to make sure, convince yourself that R and S which are appearing over here are only indices pointing along the component of vectors in the plane of the polarization, in the plane of the polarization. Okay, so now once that structure is set up, the remaining job is very straightforward. Now we have a description of A which has pointing in the plane of polarization, which is orthogonal to the plane of the projection, plane of the propagation of the wave. The A field is completely known, and from this A field we know how to compute the magnetic field and electric field in this gauge, because in this Coulomb gauge A0 is 0, the electric field is entirely the temporal derivative of this. You can take the A which is given over here, do the temporal derivative will hit only this part because everything else is time independent, and it's Hermitian conjugate over here as well. Actually this and this, the temporal derivative will be hitting, and hitting this temporal derivative will give you minus I omega p from this derivative. Remember, this involved minus I omega p, or E if you want to call it, plus ip dot x, and while its Hermitian conjugate will have the signs flipped. So when I do the derivative with respect to this, a minus iota will come out and there should be a minus overall, so I should put a minus here over there. That will come down, and plus iota omega p will come from the second term's derivative with had a minus iota p dot x, because this has a plus iota omega pt. Remember, the structure is slightly reversed. When I put a minus sign here, that means frequency or the energy function of the plane wave is appearing with a positive sign in the exponential, while in this case p dot x, I'm using the definition that energy function is coming or the frequency is coming with a minus sign. So the derivatives will throw up minus I omega t, I omega p, or plus I omega p, the temporal derivative. So this is how you will be able to compute the electric field. This has this structure. There is a relative sign difference. Similarly, when I have to obtain the magnetic field, it is curl of A. Curl of A will also be obtainable from the curl action. The curl action will just go and hit the special derivative hiding in this exponential here and there. And this will give you iota p, because remember this has a minus I omega pt plus I p dot x. So this time when I do the curl, the derivative option will bring down iota p back, and that has to undergo the curl with respect to the vector which is over here. So I have written it twice. This should not be appearing and this should not be appearing. So this curl is here and this curl is here. The curl action is going to bring down the p's out, and we will be doing the cross product, which is the character of the curl with the remaining vector which is downstairs, E lambda. Okay, so that is how we compute electric field and magnetic field from the vector potential A, its two components. Now we already knew the AIs and EJs are supposed to be conjugate pair. That means we should expect that their commutation relation, which should be upgraded version of their Poisson bracket, should give me this object. Delta x minus y, they should be on same location, and delta ij, which is this thing. This is the reminiscent of, let us say, phi I and pi j if I do at x and y. This is what this should become. My field are now AIs, and its conjugate moment are the electric field, as we have learned. So conjugation relation or the commutation relation should be this. That is what our expectation should have been. But one should take it slightly carefully. It is slightly modified relation of commutation that we will see in a minute. This delta function which is appearing over here can be written as a d3p integral of the plane wave. This is as simple, right? Now we know that if this relation is true, I have to further enforce that this AI is, or the component of EJ's electric field are not in the direction of propagation. P should be orthogonal to this or that. That information has not gone in writing this delta function over here. The delta function does not care. It is just saying in all direction plane waves with equal magnitude. That is not true for our case, because direction of P should be suppressed. It is plane wave only in the plane orthogonal to the direction of propagation. That means divergence of E and divergence of A should be 0. That has to be enforced. So that means all components I and J, it cannot take all the three components. Whatever is appearing over here should rather be R and S, and that should be RS here. So this should be the structure. If I force my vectors in the plane wave, in the plane of the orthogonal to the direction of propagation, then this orthonormality should appear with a delta RS in the momentum part. Remember, each plane wave is not a free plane wave in all direction. This is plane wave only along some plane, and orthogonality along that plane should only be appearing. That means, as we discussed, delta RS, which was the orthogonality relation of the plane, should be written as delta Ij minus Pi Pj divided by P square. So that is how my commutation relations are modified. If I insist in writing the three component AI Aj, with forgetting that one of them will be unphysical again, it can be killed off by going to a particular, it can be killed off by demanding the orthogonality relation with the propagation. If I choose my propagation direction to be z, the third component will be 0. So therefore, the commutation relation should reflect that. And that is this equation. Or if I insist in writing the three-dimensional vector, that means whatever is appearing here should be carrying the information that ultimately it is a two-dimensional story. So therefore, this delta Ij minus Pi Pj upon P square should replace the naive delta Ij expectation, where there was no constraint. If I wrote like this, there would be no constraint that P or A or P, E or P are orthogonal to each other. This will be just two quantities who are canonically conjugate to each other. Apart from that, electrodynamic story is not just the story of conjugate pair. It is the story of conjugate pair which are not free to take all directions value, and they are constrained to lie in the plane. And that is the statement that the weightage of the plane wave in the full three-dimensional space is reduced. It is projected along the plane only. So this is the projection operator in the plane in some sense. Okay, so therefore, one has to be careful that our commutation relation is this rather than the couple of lines ago where we write port like this. This would have been a commutation relation of unconstrained A and E. This is a commutation relations of constrained A and E, which are supposed to lie on a particular plane only. Okay, so then we are through. We have all the structure at our hand. Now you can verify that if I write A and E and they have to satisfy this commutation relation, which is just coming from the character of the electrodynamical field. We have demanded what? We had demanded that we are in a particular gauge where A0 is 0, divergence of A is 0, and therefore divergence of E is also 0. We are also demanding that in this gauge, the wave equation part is automatically true. Now we are saying that we can project our basis in a particular direction. The Z direction is the momentum, the propagation direction of the wave. Under this choice, only 2 degrees of freedom are left, which are R and S. And one can write down in the commutation relation like that, or in terms of, if I insist on writing the three-dimensional vector A, then this is the relation. And with that, if I want to satisfy this AEJ commutation relation, which is outcome of our demand of choices of orthonormality, and feed in this form of A and this form of E, this should satisfy the commutation relation at hand. You will be able to verify, use the definitions of A and E, which are given over here. The two D3P integrals will appear. There will be some A lambdas, E lambdas, which will be appearing in both of them. And E lambdas has a completeness relation like that. Use everything at your hand. This is a 20-minute exercise, but this is straightforward. You will be able to verify that indeed the A and A daggers again satisfy the same commutation relation they were satisfying for a harmonic oscillator all along, which we have learned. So A and A dagger, which we have written as operators as of now, indeed satisfy the same commutation relation that of an operator. So therefore, harmonic oscillator structure story is consistent with the story which we have developed. So AP of lambda, now we have two types of A's, one for lambda is equal to 1 and lambda is another for lambda is equal to 2. Remember, for a scalar field, I had only one type of AP. For the Dirac field, I had AP as a function of S, two types of AP. This time also I have a two times of AP with lambda now. This is not spin, but polarization. Okay. Ultimately, that can be tied to the spin as well of the photon, but photon being a massless spin one particle can be argued to have only two components. That is not the discussion topic of this course, but one way of looking at that is that way as well. So therefore, like Dirac operators, Dirac fields, this field also comes with two different types of oscillator, polarization 1, polarization 2. In Dirac fields, spin 1, spin 2, meaning spin half, spin minus half was there. So analogous to that, but not the same thing. This is a vector field. That was a spinor field. And all others commutator among themselves, A with A and A dagger with A dagger are 0. So all the thing which we have learned for Dirac thing, apart from its basic underlying algebra, goes through, and you know this time you will ultimately end up getting the harmonic oscillator Hamiltonian again back as well. So H will be this, just like we have done the number operator plus an extra with a positive sign, the divergence term which we have been getting all along as well. This time it is again a bosonic field, you will get a plus over here, and ultimately in the normal ordered form, if you have to discuss, you can discard this term. This is all the excitations which we will discuss will be above this minimum value the Hamiltonian can take. The excitations are supposed to be above this piece which is divergent in nature. And the same game, like a vacuum of the theory is vacuum of all oscillators ground state. The oscillators are of various different momenta, and they come with different polarization angle lambda as well, polarization component lambda. Previously in spin case, it was P and spin product. Which oscillator with what spin? Now we are talking about which oscillator with what polarization. So this is the same story after all, and therefore all this techniques what we have learned will be applicable here as well. So we have a similar to Dirac field story, a two-component object, but vector component. There it was a spinor component, and it is coming with a polarization vector. The wave is proportional to E lambda with some operator over here. Previously, the Dirac field was proportional to two-component object with a complex spinor coming along. So E lambda has morphed into the spinor has been morphed into E lambda. Operator is still two-component operator, which is previously it was spin dependent operator at a particular P. This time it is polarization dependent operator at a particular P. So therefore, whatever we have learned for scalar field and Dirac field goes through, and we have the same structure, and we know how to quantize the electrodynamic field in the same way that we have been quantizing all along. So I stopped the discussion over here. This has given you just a glimpse of how things are quantized for electromagnetic field, and that is what we adopt to. And we will move forward from in the next class onwards. Once we have seen how to quantize different fields, we will know about what is the properties of interesting states in that, and what is the expectation value of various things, which will come handy when we try to couple these fields to the atoms which we had discussed in the first part of the course. So I stop here.